Welcome to this custom-tailored deep dive designed specifically for you.
We know exactly who you are, too.
Exactly. You're a curious learner, you love to grasp complex ideas quickly, you want to be well-informed, and, well, you absolutely hate drowning in unnecessary jargon.
Nobody wants that.
Right. Nobody wants that. You want the insight, the multiple perspectives, and those really satisfying aha moments without feeling like you're sitting through some dry university lecture.
Which this definitely isn't.
Definitely not. That is exactly what we are here to deliver today. Our mission for this deep dive is, well, it's pretty ambitious. We are taking a massive stack of mechanical engineering textbooks.
Dense sources.
Very dense, covering systems engineering, mathematical modeling, thermodynamics, fluid mechanics, heat transfer, and energy conversion. And we are going to distill them into clear, practical knowledge. Okay, let's unpack this.
It really is a wonderful challenge to tackle, because looking at this stack of sources, it is very easy to see it as just an overwhelming mountain of equations and technical diagrams.
Oh, for sure.
Yeah.
It looks terrifying at first glance.
It does, but when you look closer and kind of step back from the raw math, it's actually this beautiful interconnected rulebook. It's the fundamental code for how the physical universe operates.
The code of the universe.
Exactly. And more importantly, it shows us exactly how engineers harness those fundamental rules to build the modern world around you.
I really love that perspective. It's not just math on a chalkboard, it's the operating system of reality. And to understand how engineers use that operating system, we kind of have to start with the big picture.
Right, the macro view.
Yeah. So let's talk about systems engineering. I was actually a bit surprised looking through our sources, because I always thought mechanical engineering was just about, building physical machines. But the sources define systems engineering as a management technology.
Yes, they do.
So why does a mechanical engineering textbook start with management?
Well, it's a crucial starting point because pure science means very little if it cannot be organized and delivered for the betterment of humankind. Systems engineering is where the pristine laws of physics meet the incredibly messy reality of human organizations.
And budgets and natural environments, right?
Precisely. It is a discipline specifically designed to deal with imperfect information. Think about it in the real world. You never have every single piece of data you might want before you are forced to build something.
You just have to make a call.
You have to make calculated decisions.
So it's a framework for making sure you're even building the right thing in the first place.
Precisely that. The sources detail a very structured three-step framework for managing this complexity before anyone ever touches a wrench or drafts a blueprint.
Okay.
The first step is issue formulation.
Okay, so what does issue formulation look like in practice? Is that just writing down the problem?
It goes deeper than that. It is about identifying the actual needs and constraints. It's asking, what fundamental problem are we trying to solve? If a city says they need a new bridge, issue formulation asks if they actually need a bridge, or if they just need a better way to move people across a river.
Ah, I see. So a ferry or a tunnel might be the better answer.
Exactly. You have to define the correct target.
That makes a lot of sense. And then what?
Then comes issue analysis. This is where engineers determine the impacts of different alternatives. Like, if we build a suspension bridge versus a truss bridge, what happens to the traffic flow?
What happens to the local environment?
Right. Finally, the third step is issue interpretation, where they take all that analysis, rank those alternatives based on the original constraints, and select the best path forward. It is highly analytical decision-making.
Right, so once those high-level decisions are made, and they know what they actually need to build, engineers have to figure out how to represent physical reality in a way they can actually calculate.
Yes, they need a model.
Yeah, and I was reading about this concept in the sources called lumped parameter models. I kind of get it, but could you give me an explained, like I'm five analogy for this? Because the universe seems way too complex to just put into a single equation.
The universe is incredibly complex, which is why engineers have to cheat a little bit by simplifying it.
Cheating for science.
Essentially, yes. If you are trying to design a car's suspension, you cannot calculate the behavior of every single iron atom in the shock absorber. It would take a supercomputer thousands of years.
Right.
So instead, they lump the properties together into what they call ideal elements. They strip away the messiness and pretend the suspension is made of a pure mass, a pure spring, and a pure damper.
Okay, so they create a simplified mathematical cartoon of the real world.
Exactly. And the genius of this approach is that it unifies completely different physical systems using just two primary types of variables.
Just two.
Just two. First, you have through variables. These represent quantities that are transmitted directly through an element. Think of mechanical force pushing through a rod, electrical current flowing through a wire, or fluid flowing through a pipe.
Got it. Force, current, flow.
Right. Second, you have across variables. These represent a difference in state across the element itself.
Like a difference between point A and point B.
Exactly. Such as a velocity difference between two ends of a shock absorber, a voltage drop across a resistor, or a pressure difference across a valve.
So by stripping everything down to just through and across variables, they are basically creating a universal mathematical language.
They absolutely are. Let us look at how they represent the state of a system mathematically using phase variables. The sources describe this very clearly.
How does that look?
If we have a dynamic system where the output is y, we can define the phase variables by setting up a sequence of equations. We would say x sub 1 as a function of t equals y as a function of t.
Okay, that's the first variable.
Then, the next variable, x sub 2 as a function of t, equals the derivative of y with respect to t. We can continue taking derivatives to track the system's acceleration, jerk, and so on for higher order systems.
So by taking those derivatives, they get a clean, uniform way to track the exact state of the system as it changes over time.
Yes, what's fascinating here is how this creates a truly universal language across engineering disciplines. Because the math is exactly the same, a mechanical suspension system made of a mass, a spring, and a damper has a direct mathematical analog in an electrical circuit made of an inductor, a capacitor, and a resistor.
Wait, really?
Truly.
You're saying the math equation doesn't actually know if it is describing a bumpy road hitting a tire or a power surge hitting a computer circuit?
The math is entirely blind to the physical materials. The equations do not care if they're describing steel and hydraulics or copper wire and electricity.
That is wild.
A sudden jolt of voltage mathematically ripples through an electrical circuit the exact same way a pothole ripples through a car's chassis.
That blows my mind. The exact same mathematical model solves the bouncy car and the buzzing circuit.
It does.
Well, if mathematical modeling is the language engineers use, it seems like thermodynamics is the ultimate accounting ledger they are forced to balance. The sources make it very clear you cannot cheat the universe.
You certainly cannot. The first law of thermodynamics is the ultimate statement of energy conservation.
The classic rule.
Right. For a closed system, the math dictates that the net heat transfer into the system equals the work done by the system on the environment plus the increase in the energy of the system. It is a strict balancing act. Energy cannot just vanish into nowhere. It simply changes forms or moves around.
Right. It's just shifting funds from checking to savings, so to speak, except we are talking purely about joules of energy.
That's a great way to think of it.
But the second law of thermodynamics is where the harsh reality of the universe sets in. It introduces the concepts of irreversibility and entropy. It tells us that while the total amount of energy is conserved, the actual usefulness of that energy is constantly degrading. You can never break even.
That is the tragedy of the universe in a nutshell, and the sources give us the absolute mathematical limit of how efficiently we can ever convert heat into useful work.
And that's the Carnot efficiency.
Yes. To calculate the absolute maximum possible efficiency of an idealized heat engine, the equation is strict. Efficiency equals the difference between T sub hot and T sub cold, all divided by T sub hot.
Okay, let me make sure I'm grasping that. You take the hottest temperature in your engine, subtract the coldest temperature of the outside environment, and divide that by the hot temperature.
Right.
So mathematically, you can never reach 100% efficiency unless your cold reservoir is at absolute zero, which is physically impossible.
It is impossible. You will always lose some heat to the surrounding environment. And that brings us to one of the most profound concepts in the sources, exergy.
Exergy, with an X.
Yes. Exergy is defined as the maximum available work you can extract from a system as it comes into equilibrium with its environment. It is a measure of pure potential.
Okay.
But because of the second law of thermodynamics, every real-world process destroys some exergy. It generates entropy.
So exergy is the useful stuff, and entropy is the waste,
Yeah.
and the universe is constantly demanding its cut of entropy.
Exactly. It's a universal tax. And modern engineers fight back using a technique called entropy generation minimization, or EGM.
How does that work?
They use EGM to relate that thermodynamic non-ideality directly to tangible physical realities, like finite dimensions, shapes, and materials.
Wait, so they're literally designing the physical shape of a machine, like the curve of a pipe or the thickness of a wall, specifically to fight back against the decay of the universe.
That is exactly what they are doing. They are trying to waste the absolute minimum amount of energy possible by optimizing the geometry of the machine.
That is incredible. It is philosophical accounting applied to solid steel.
I like that phrasing.
And speaking of shaping that steel, that leads us perfectly into how things flow around those shapes. Fluid mechanics.
A huge topic.
Yeah, when I think of fluid mechanics, I usually picture wind blowing over a mountain or water rushing through a gorge. But the sources show engineers have to be mathematically precise about how those fluids behave.
They do. They divide the study into fluid kinematics, which is just the motion of the fluid itself, and fluid momentum, which involves the forces. Now, to describe exactly how a viscous fluid behaves, they rely on the Navier-Stokes equations.
Let's define viscous for a second. We are talking about the thickness or stickiness of a fluid, right?
Yeah.
Like honey being more viscous than water.
Correct. Viscosity is essentially fluid friction. The Navier-Stokes equations account for that internal friction, but they are incredibly complex differential equations.
How complex?
Well, they are so notoriously difficult that finding a general mathematical solution for them is one of the greatest unsolved problems in physics. So, for simpler cases, engineers make assumptions. If they assume the flow is steady and irrotational, meaning the fluid particles are moving smoothly without swirling or spinning like tiny tornadoes, they can use the Bernoulli equation.
Ah, Bernoulli.
Yes. The Bernoulli equation elegantly shows how a fluid's velocity, pressure, and elevation all trade off against one another.
And when they want to test a design, like a new airplane wing, they don't just build a massive jet right away. They use scale models and wind tunnels.
Of course.
But I've always wondered, you can't just put a tiny 6-inch plastic toy airplane in a wind tunnel and magically get the aerodynamic data for a Boeing 747, right? Because the air molecules don't shrink down to scale.
No, they do not, and that is a brilliant point. The physics of the air flowing over a tiny model are fundamentally different than the air flowing over a massive jet, unless you force the math to match.
How do you do that?
To ensure the tiny model behaves mathematically the same as the real thing, engineers rely on dimensionless numbers to achieve what is called dynamic similarity.
Dimensionless numbers. So these are ratios that cancel out units like feet or seconds, leaving just a pure number.
Yes. These numbers tell you which physical forces are dominating the flow. For example, the Reynolds number is the ratio of inertia force divided by viscous force.
Okay, so inertia versus friction.
Right. If the Reynolds number is low, the flow is smooth and orderly. If it is high, the flow is chaotic and turbulent.
Makes sense.
Another key one is the Froude number, which is the inertia force divided by the gravity force. This one is crucial for designing ships because it dictates how waves form around the hull.
Right, because gravity is pulling the waves down.
Exactly. And finally, the Mach number is simply the velocity of the fluid divided by the local speed of sound, which defines the massive aerodynamic jump from subsonic to supersonic flight.
Here's where it gets really interesting. All of these massive, sweeping fluid concepts, whether it is a submarine displacing water or a jet going Mach 2, all come down to what happens right at the microscopic surface of the object, the boundary layer.
The boundary layer is where all the action happens. It is the incredibly thin region of retarded fluid flow right next to a solid boundary. The fluid molecules actually stick to the surface.
They just grab onto the metal.
They do not move at all, and the layers of fluid just above them have to slide over each other, creating intense friction and drag.
So the entire science of aerodynamics is basically an obsession with controlling that tiny, invisible layer of friction hugging the metal.
It is, and naturally where there is intense friction, there is heat.
Which brings us to our next major topic.
Controlling what happens at that surface inevitably means dealing with moving the energy, or heat transfer. We know from basic thermodynamics that heat always wants to move from a hot area to a cold area.
Right.
But heat transfer is the engineering science of calculating exactly how fast it moves and how to control it.
Right, because the application changes everything. If you're designing a computer chip, you need heat to race away from it as fast as possible so the silicon doesn't melt. But if you are designing a winter coat, or the stick walls of an industrial furnace, you want to stop heat dead in its tracks.
Yeah.
So how do they actually calculate that movement?
They break it down into 3 distinct modes of heat transfer, and the mathematics for each is incredibly strict.
Let's hear them.
The first mode is conduction. This is heat transfer through direct molecular impact without the material itself moving. Think of heat traveling up a metal spoon sitting in a hot cup of coffee.
Okay, full enough.
The governing rule here is Fourier's law of heat conduction. The equation states Q sub x equals negative K times A times the derivative of T with respect to x.
Okay, let's look at that K in the equation. That is the thermal conductivity of the material, right?
Yes.
That explains why the metal spoon burns your hand, but a wooden spoon doesn't. Metals have a very high K value, meaning they are eager to pass the heat along, while wood or plastic are insulators.
Precisely. Now, when a solid object like a hot piece of metal is suddenly exposed to a cooling fluid, engineers use a dimensionless parameter called the buyout number to figure out what happens inside the metal.
Another dimensionless number.
Yes. The equation is Bi equals H times L divided by K. This compares the heat transfer happening at the surface due to the fluid to the internal conduction moving heat through the solid itself.
Why does that comparison matter?
Because if the buyout number is less than 0.1, it means the internal conduction is so incredibly fast that the solid's temperature is practically uniform throughout its entire volume. It cools down all at once.
Oh, I see.
For more complex transient heat problems, meaning situations where the temperature is actively changing over time, rather than holding steady, engineers rely on specialized graphical tools called Heisler charts to find the solution without doing pages of calculus.
I'm sure the engineers appreciate not doing pages of calculus.
They do?
Okay, so conduction is heat moving through solid stuff. The second mode is convection, which is heat transfer involving actual fluid motion. This is the wind cooling you down on a freezing winter day.
For convection, engineers use Newton's law of cooling. The relationship is elegant. Q equals H times A times the difference between T sub S and T sub F.
What's the H stand for?
The H is the convection heat transfer coefficient, and it depends heavily on how the fluid is moving. Engineers broadly divide this into two categories. There is forced convection, where a physical mechanism like a pump or a fan is forcefully pushing the fluid over the surface.
Like a PC cooling fan.
Right. Then there is free convection, where the fluid moves naturally entirely due to buoyancy. The heat changes the density of the fluid, causing hot air to rise and cold air to sink, creating its own flow.
And the third mode is radiation. This is the heat you feel radiating from the sun or from glowing red-hot metal in a forge. It travels through electromagnetic waves.
Which means it doesn't even need air or water to carry it.
It can travel straight through the vacuum of space.
It is a completely different mechanism. The mathematics of radiation for ideal radiating bodies in a vacuum is governed by the Stefan-Boltzmann law.
How does that one go?
The equation is Q equals sigma times S times script, F times the quantity T sub 1 to the fourth power minus T sub 2 to the fourth power.
Wait, raised to the fourth power. Let me think about that. If you double the absolute temperature of an object, two times 2, that is 16 times the heat radiation.
Your math is spot on. Because the temperature terms are raised to the fourth power, radiation grows exponentially.
That's huge.
It is. At room temperature, radiation is often negligible compared to convection. But at very high temperatures, like inside a jet engine or a furnace, radiation suddenly becomes the absolutely dominant mode of heat transfer.
That is a brilliant aha moment. No wonder you can feel the heat of a bonfire on your face from 20 feet away. Now, when you take all three of these heat transfer modes, engineers can build some truly fascinating physical devices. One of the coolest mentioned in the sources is the heat pipe.
Ah, heat pipes.
It is described as a hollow tube that can move heat far faster than a solid piece of copper ever could. How does a hollow tube beat solid metal?
Heat pipes are an elegant application of thermodynamics and fluid mechanics working together. They consist of three distinct regions: an evaporator section at the hot end, an adiabatic section in the middle.
Adiabatic?
Adiabatic simply meaning it is heavily insulated so no heat is lost to the outside.
Got it.
And a condenser section at the cold end.
And what is inside this tube?
Inside, there is a small amount of working fluid and a porous wick structure lining the walls. When heat enters the evaporator, it instantly boils the liquid into a vapor.
So it flushes to steam, essentially.
Yes, and that vapor races down the hollow center of the tube at high speed toward the condenser. When it hits the cold condenser, it releases its massive latent heat of vaporization and turns back into a liquid.
But then how does the liquid get back to the hot end to start over? Does it need a pump?
That is the genius of the wick. Capillary forces in the wick literally pull the liquid back to the evaporator, much like a paper towel soaking up water against gravity,
Wow.
because the entire process relies on phase change boiling, and condensing it operates as a nearly isothermal device. This means the temperature stays incredibly uniform from end to end, making it a high-speed highway for heat, completely silent, with zero moving parts.
That is just brilliant engineering. Which brings us to the final part of our deep dive, powering the world through energy conversion systems. It is one thing to look at these laws of thermodynamics and heat transfer on a chalkboard, but it's another to realize how they culminate in the massive machines that keep our lights on and our vehicles moving.
If we connect this to the bigger picture, all of this theoretical physics only exists to serve human needs. Let us look at gas turbines, which operate on the Brayton cycle.
The Brayton cycle.
This is a continuous flow process. Imagine a jet engine. Air is continuously drawn into a spinning compressor to radically raise its pressure. Then it flows into a combustor where fuel is burned, adding massive amounts of heat energy. Finally, that hot, high-pressure gas expands violently through a turbine, spinning it to create mechanical work.
And the performance of these gas turbines comes down to a few key parameters, right? The mass flow of the air moving through it, the pressure ratio the compressor can achieve, and the firing temperature inside the combustor.
Firing temperature is the critical bottleneck. Higher firing temperatures exponentially increase both the power density and the overall thermodynamic efficiency of the turbine. But of course, you hit a physical limit.
The melting point of the metal turbine blades.
Exactly. Going back to heat transfer, you have to keep the metal from melting while it is sitting in a literal stream of fire.
That sounds impossible.
It requires incredible heat transfer engineering. Modern turbine blades actually have intricate cooling channels cast inside of them, bleeding cool air out of tiny holes to create a protective boundary layer of cool air over the metal surface. It is a masterpiece of applied fluid dynamics.
That's amazing.
You also see a massive difference in how these turbines are built depending on their application.
Yeah, the sources pointed out that aircraft jet engines, which operate on the same Brayton cycle, prioritize a high power-to-weight ratio. They have to fly, so they use thin, highly engineered machined casings to save weight.
Naturally.
But an industrial gas turbine sitting bolted to the floor in a power plant does not care about weight at all. It cares about running for 30 years without breaking, so they use incredibly heavy, thick cast casings.
Now let us contrast that continuous Brayton cycle with steam turbines, which operate on the Rankine cycle. The key difference here is that the Rankine cycle utilizes a phase change.
So boiling water.
Right. Water is boiled into high-pressure steam in a massive boiler, expanded through the turbine to extract work, and then condensed back into liquid water in a condenser to be pumped back to the boiler.
To actually get rotational power out of that high-pressure steam, the turbine blading has to convert thermal energy into mechanical energy by changing the fluid's momentum. I read that they literally curve the metal blades to catch and redirect the steam.
Yes, the engineering of those blades is governed strictly by Newton's laws of motion applied to the flow passage between adjacent blades. Engineers treat that empty space between the blades as a stream tube.
A stream tube.
Yes. By analyzing the mass and momentum of the fluid entering and leaving that stream tube, they can calculate the exact rotational force exerted on the turbine rotor.
That brings us to the engines most of us interact with every single day. Internal combustion engines, or IC engines, in our cars and trucks. These use the Otto cycle for standard gasoline engines and the diesel cycle for diesel engines.
Regardless of the specific thermodynamic cycle, these reciprocating engines all go through 5 fundamental processes: intake of fresh air, compression of that air, combustion of fuel to release heat, expansion to push the piston down and do actual work, and exhaust to push the spent gases out of the cylinder.
The diesel cycle specifically caught my eye because it does not use a spark plug. It relies entirely on the heat of compression to ignite the fuel. How hard do you have to squeeze air to make it hot enough to start a fire?
You have to squeeze it incredibly hard. In a diesel engine, only pure air is drawn in during the intake stroke. During compression, that air is compressed to a massive 450 to 650 psi.
Wow.
Because it is squeezed so tightly and so quickly, the internal energy spikes and its temperature skyrockets to at least 500 degrees Celsius.
That's from being squeezed.
Yes. Right at the very top of the stroke, atomized liquid fuel is injected directly into this superheated air, and it ignites instantly on contact, entirely due to the temperature of the compressed air.
And what exactly happens chemically during that combustion? Engineers don't just guess how much fuel to squirt in. They map it out using combustion stoichiometry. This is the exact chemical recipe required for a perfect clean burn. The sources give a great concrete example for burning methane.
The stoichiometric equation for methane combustion is mathematically precise. It dictates that 1 volume of CH4 plus 2 volumes of O2 yields 1 volume of CO2 and 2 volumes of H2O. It allows engineers to calculate the exact air-to-fuel ratio needed.
Which connects right back to everyday life. If your car's oxygen sensor breaks, the engine's computer loses track of that exact stoichiometric ratio. It might dump in too much fuel, running rich and wasting energy, or too little fuel, running lean and losing power. Getting that chemical math perfectly right is the difference between safe exhaust and pumping deadly carbon monoxide into the air.
Exactly. It is a perfect example of theoretical chemistry dictating practical mechanical design.
So what does this all mean for you? We have gone on an incredible journey today. We started with the abstract math of systems engineering and lumped parameter models, where bumpy roads and electrical circuits show the exact same equations.
Such a great concept.
We navigated the strict, unforgiving laws of thermodynamics and fluid mechanics, and we ended up in the roaring, high-pressure reality of gas turbines and diesel engines. The major takeaway is that theoretical laws, like the Carnot efficiency, dictate the absolute, unbreakable limits of the physical universe. But engineers use their mastery of fluid dynamics and heat transfer to push physical machines as brilliantly close to those limits as reality will allow.
Knowledge is most valuable when it is understood and applied. Understanding these principles allows you to look at the engineered world with entirely new eyes. From the simple refrigerator humming quietly in your kitchen, moving heat against its will, to the massive jet engine flying you safely across the world, they are all strictly obeying the invisible rules we discussed today.
It really makes you appreciate the built environment so much more. You are not just seeing a metal machine, you are seeing applied physics, a physical shape actively fighting against the entropy of the universe.
This raises an important question, though. Since the second law of thermodynamics dictates that entropy must always increase, and every single energy conversion inevitably destroys some exergy or available work, are the ultimate limits of human technological progress bound not by our creativity, but by the inescapable thermal accounting of the universe?
A universal tax.
Yes. How might future engineers completely bypass these thermal cycles to extract work without paying the universe's tax? It is a profound challenge for the next generation of problem solvers.
That is a phenomenal thought to leave off on. We are strictly bounded by the universe, but human ingenuity is always looking for the next loophole. Thank you for joining us for this deep dive. Keep looking at the world around you, keep asking how it works, and keep questioning the limits of what is possible.